Hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at UberETG as well as a professor at the University of Toronto. In this talk, I'm going to talk about human in the loop in the context of self-driving. In particular, I will touch on explainability for building end-to-end trainable autonomy systems, on how machines and humans can collaborate to understand logs captured by the fleet, as well as create labels and high-definition maps at scale. Let's begin by discussing explainability in the context of self-driving. A very popular approach in academia is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, LiDAR or images, and the output is the information necessary for the self-driving car to drive. For example, steering command and acceleration. The advantage of such an approach is that it is very easy to get a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge, and thus make this system respect the rules of traffic. It also has no interpretability, which poses a problem for the system's validation and safety. An alternative is the traditional software stack, which is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it is easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Our vision, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting their respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is not shared across modules, the resulting reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. In the following, I will present three different efforts in this direction. Our first work is the end-to-end interpretable neural motion planner, published at CVPR 2019. It uses a deep neural network to produce a learned cost volume and improves the performance of the deep network with auxiliary detection and prediction tasks. Later, we propose DSDNet, Deep Structured Self-Driving Network, which further improves performance and interpretability by outputting non-parametric multimodal predictions and planning condition of these predictions. The third work investigates how we can bypass detection post-processing, which may lose useful information. Now, let me briefly explain the main idea behind each one of these works. Our first attempt frames the problem as multitask learning. The input to our model is raw sensor data in the form of LiDAR point clouds and an XD map, which are fed to a CNN in order to extract useful features. To produce intermediate representations, our model outputs detections on pretty fine anchor boxes. It also predicts each actor's future trajectory simultaneously and motion planning as a cost volume. The value of each pixel in this volume represents the cost for the echo car to be at that location at future timestamp, where different timestamps are encoded with different channels. Lower cost regions are preferred. During inference, we use a physically valid trajectory sample to sample a wide variety of trajectories. These trajectories are guaranteed to follow vehicle dynamic constraints. We then evaluate the cost of each trajectory using the cost volume and select the one with the minimum cost. We train our model end-to-end with a multitask loss, including detection, prediction, and motion planning losses. For detection and prediction, we use standard classification and regression losses. For planning, since we do not have run-through supervision for the cost volume, we utilize imitation learning and encourage trajectories to have low cost if they are close to the expert demonstrations. We also penalize trajectories that collide with objects or do not follow traffic routes. Here we show our results. Compared with the state-of-the-art, our model achieves on par or even better detection and prediction performance at the time of publication. More importantly, as we can see in the figure, our planning results have a much lower collision and lane violation rate, which indicates safer planning. Let's look at qualitative results. Our model takes LiDAR and HD maps as input and outputs detection, prediction, as well as motion planning cost volume. We highlight the low-cost regions for different time steps using different colors. Our planned trajectory is shown in red, and the ground truth trajectory is shown in blue. As you can see here, our vehicle prefers to follow the line perfectly. Note that our cost value captures multimodality. In this case, we can see that we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockage. The cost variant shows a preference to lane change in order to avoid collision. Here are two examples of super nudging in heavy traffic. This is one of the most difficult maneuvers in self-driving. As shown in MMP, sharing computation among all three tasks allows us to perform full inference within a few milliseconds, and also maintain interpretable intermediate representations. However, there are still two major weaknesses of this work. First of all, the feature is at times very uncertain. For instance, for this highlighted car, it will either turn right or go straight. Moreover, different actors interact with each other and follow traffic rules, such as yielding and not colliding. Therefore, a multi-agent prediction with calibrated multimodal uncertainties is necessary for safe planning. Second, although NMP, which is our previous work, is able to predict the future, its planning model is not explicitly conditioned on the prediction output, which may cause some inconsistent planning results. To address these limitations, we propose DSDNet, a deep structured neural motion planner that jointly reasons about perception, forecasting, and motion planning. Specifically, our method has several advantages. First, computation is shared between models. Second, our method explicitly models socially consistent multimodal uncertainties in the future trajectories of the traffic participants. And finally, our learning-based planner leverages the power of deep learning and takes traffic rules into consideration, as well as in order to guarantee safety. Of particular interest in this work is our prediction model, which exploits deep learning to compute complex unary potentials and encode prior knowledge in the pairwise potentials, penalizing, for example, collisions. Inference is performed by a forward pass followed by belief propagation. Motion planning is similar to the previous model, with the exception that we exploit the marginal distributions over trajectories provided by the output of the prediction model, and we also use a mixture of hand-coded costs for safety as well as learn costs. Here we first report our prediction performance. We compare our multimodal socially consistent prediction method against several state-of-the-art methods on a number of datasets. Here we show the results of two publicly available datasets, Musins and Brico-Carla. We achieve significantly better prediction error. Our method also achieves a near zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. Here we show our planning results. Again, we compare against an end-to-end imitation learning approach, as well as our previous NMP method. Our DSD approach achieves significantly better performance in terms of collision and lane violation rates. This is due to the fact that now our model specifically considers multiple future possibilities and then plans a safe trajectory that is compliant with the other actors' future behaviors. Now let's see some qualitative results. In this figure, each blue box represents an object, and its dotted line represents its most likely future prediction. We visualize the model asserted the estimates with a dense color map. Different colors represent different times. Note that this is prediction now, not as in the NMP visualization that was actually motion planning. Our algorithm is able to capture all the possibilities for the car approaching an intersection. This is a good thing. It suggests that our motion planning will take all possible features into consideration when planning its trajectory, not just one. Here we see, here is one more result of motion forecasting. We can see that far away and turning objects, we are more uncertain of the future. On the other hand, for objects that are going straight along the lane and close to us, our model is quite certain. Next, let's see some planning results. Here we show a scenario in which our ego car follows a curved lane very well. This is a turning scenario. Here you can see that our planned trajectory is smooth and follows the lane structure very well. This is a situation in which a parked car blocks the ego car's lane. Thus, our planner nudges around the parked car to avoid collision. Here is a short demo. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving on a straight line, our model is more certain about its direction, but a bit uncertain about its future velocity. Here is an example where we perfectly predict that the leading vehicle is stopping, and we plan a nudging trajectory to avoid collision with the parked car. This shows that our model can follow the lane perfectly. Here is the nudging behavior. So far, we have discussed two efforts on how to improve interpretability for end-to-end neuromotion planning. Both of these works detect surrounding actors first, and then conduct planning based on detection results. For example, in this case, the self-driving car situated in the bottom will know a coming vehicle is crossing its left turn lane, and thus will yield to the car. However, detection requires post-processing and only reflects an actor if his detection score exceeds a certain threshold. But what if the detection score becomes below the threshold and the ego car misdetects the vehicle? This might cause a severe collision, which is of course something we don't want to see. We tackle this issue by designing a novel end-to-end approach that predicts and plans. The overall idea is very simple. Rather than performing object detection and then predicting trajectories for each object, our model directly generates semantic feature occupancies. These occupancy forecasts are scene-based and instance-free, and hence our approach does not require thresholding of detection scores or performing NMS, no mathematical regression, thus increasing safety. The planner uses these non-parametric spatiotemporal occupancy maps, along with other interpretable codes, to plan an explainable trajectory that is safe, comfortable, and respects traffic rules. Note that the entire model can be trained end-to-end since all the components are differentiable. Let's deep dive a bit into the exact intermediate representations we use. We consider vehicles, pedestrians, and bikes as the classes we want to predict their occupancy. Note that it's easy to extend this to other classes in the future. To make the representation more interpretable, we subdivide them semantically as shown in the hierarchy. For pedestrians and bikes, we only differentiate between visible or partially visible, meaning that they have one or more later points on the surface and are occluded. For vehicle, we subdivide them into park, on conflict lane, oncoming traffic, on the route, occluded, and others. This subdivision allows us to learn different weights for the motion planner subcodes corresponding to different subcategories. For instance, we do not need to keep the same safety buffer if we know a car is parked, then if a car is in the conflicted traffic. Now that we assume vehicles, pedestrians, and bikes to be independent, since we can find cases where a small region of space is occupied by more than one class. For instance, a pedestrian getting out of a car. The subcategories within each root category are considered mutually exclusive. Similar to previous works, we take a history of voxelized LiDAR strips and a raster map of the scene as input, and we extract LiDAR and map features with a TrueStream CNN and fuse them by concatenating them and adding a subsequent CNN. Finally, a recurrent occupancy update predicts the semantic occupancies into the future. As you can see, there is no post-processing at the actor level. This is another advantage of our method since the computation cost does not increase in more cluttered scenes, which is important for real-time applications like ours. To obtain smooth occupancies over time, we leverage a special memory and a CNN-based update that only predicts the residual with respect to the previous occupancy. The planner samples a set of trajectories. A cost function is used to evaluate each trajectory considering different aspects of driving. The best trajectory is then selected for execution. The criteria to select the best trajectory is composed of several interpretable cost functions and a learnable aggregation. For instance, the spatiotemporal occupancy map are used to penalize trajectories that overlap partially occupied regions. Another aspect of driving that is included in our cost function is the route. Trajectories that are moving forward towards the lanes that eventually diverge from the roads are penalized. We also take into account the smoothness and comfort of the trajectories in the cost functions. For example, trajectories that are turning at high speed will cause large lateral acceleration and are not pleasant for the riders. Such trajectories will get penalized. Here is a video that shows examples of predicting semantic occupancies and open-loop plan trajectories. The semantic classes are color-coded according to the legend on the top right. The empty boxes indicate ground truth objects and SDV. Our model is able to capture multimodality of future occupancies caused by each vehicle. The generated trajectories avoid occupied regions and stay within the lanes. The model is also able to pick occluded regions indicated by cyan color. Fundamental for self-driving is the data utilized to train the models as well as to test them. Next, we will discuss log understanding for self-driving. Self-driving companies have accumulated massive databases of raw data logs from driving millions of miles in the real world. To make use of this data most effectively, it is crucial to develop powerful log understanding systems such as automatic log tagging. Amongst its applications, tagging logs with described metadata enables the retrieval of thousands of variations of interesting scenarios to stress test our autonomous system. Advanced analysis of failure modes by visualizing tags most correlated with system failure, and the rapid creation of interesting data sets for training new models. Importantly, machine learning models for automatic tagging very naturally benefit from a human-in-the-loop setting, as the tags produced by the model can be used to retrieve interesting examples, which can be quickly filtered for correctness by humans, providing new supervision used to continuously improve model performance. Same applies to select the scenarios from which we can create simulations in a semi-automatic manner. Let's consider now some potential approaches for trying to solve this problem of log tagging. The simplest option is to use humans with no help from computers to manually tag scenes with descriptive annotations. While this approach can be effective on very small datasets, it does not scale to self-driving databases containing millions of miles, as it is far too expensive and time-consuming. Alternatively, the output from the onboard perception system can be reduced to heuristically reason about different scenarios based on the detections over time. Unfortunately, this approach requires extensive engineering, often returns noisy results, and cannot generalize to many scenarios which require reasoning beyond that of detections. Finally, we could consider building a natural language Q&A system, using the model's answers to generate a set of tags. While in theory, natural language can express questions relating to any attribute in the scene, it also introduces extra complexity and is therefore suited for the real-world setting of log tagging. Motivated by the shortcomings of these approaches, our goal is to build a system which takes only raw sensor data as input learns a single model for a complex and varied set of queries, yet uses a structured format to avoid the complexity of natural language questions. To achieve these goals, we introduced the novel task of structured question answering for self-driving. Given raw sensor data from a self-driving log, our task is to answer structured queries, represented by three components: QX, QR, and QP. QX is the query attribute, which can be any continuous or discrete attribute in the self-driving scene. Examples of these attributes are vehicle actions like turning or map attributes like intersection time. QR is the query region of interest. As an example, the user can set QR to be the region in front of the SDB, shown in the figure on the right. Finally, QP references a pooling function, which specifies how values are pulled across the region of interest. Depending on the context of the query, we may either want to sum or pull values across QR. This task is challenging to solve efficiently due to sensor noise, the special reasoning required to handle explicit regions of interest, and the complexity of supporting a large and varied set of attributes within a single model. We carefully design our approach to overcome these challenges. We learn a single data log embedding from raw sensor data, used to answer our queries. Attributes are represented by learn embeddings, allowing similar attributes to learn similar attribute representations. Our design ensures that our model can be used to efficiently answer many queries, since log embeddings can be pre-computed once and cached for future queries. Our embedding maintains special dimensions so that the query's regions of interest and pooling function can be applied directly. Let's now showcase some examples of attributes QX we want our system to be able to reason about. First, we consider the actual density of the scene. For any spatial region, we can count the number of vehicles or pedestrians. Here we show an example of a particularly dense scene with many vehicles and many pedestrians. These scenarios can be particularly interesting for the evaluation of prediction and motion planning models. We also consider the actions performed by any agent within the scene. This includes whether each vehicle is stopped, braking, park, lane changing, or turning. For pedestrians, we consider actions like walking along the sidewalk and crossing the street. In addition to actions, we consider a diverse set of labeled interactions, including stop for, braking for, and yielding to other actors. Along with these discrete attributes, we also consider continuous attributes of the scene, such as each vehicle's current speed. Finally, we consider queries which relate to the map topology. Next, we will describe our model, which can efficiently answer queries related to this diverse set of scene attributes from only raw sensor data and HD maps. Our log embedding network learns a universal spatial embedding for each timestamp. The fully convolutional network takes a series of voxelized letter sweeps and a rasterized HD map and produces an embedding. Importantly, our embedding is spatially aware and maintains the original spatial dimensions downsampled at a rate of R. We use this embedding E to answer all queries. Now, imagine we are given a structured question which encodes, is there a vehicle turning left in front of the SDB? First, we encode the attribute QX, which in this case corresponds to the predefined left turn attribute. To represent the attribute, we simply look up its corresponding row in the learnable matrix K. Our answering model takes both the universal embedded E and the attribute embedding as input. Using a simple element-wise dot product, we obtain a spatially aware answer map, capital A. Finally, we put the results over the spatial region of interest. In our example, this corresponds to the region in front of the SDB. Results are pulled using a pooling function specified by the query, returning an answer, lowercase a. Our approach is trained end-to-end to minimize a supervised query loss across the 15 attributes described earlier. Our model can also be extended to handle compositions through the use of compositional functions. These functions take a set of spatial answer maps from multiple attributes as input and returns a new answer map. Compositions enables our model to naturally handle more complicated queries that relate to multiple attributes. For example, find any scenes with vehicles turning at a three-way intersection. As shown in this example, we also use compositional queries to break down the recognition of vehicle actions and interactions into two simple subtasks: recognizing the existence of a vehicle at a particular location through vehicle density, and two, reasoning about the vehicle action condition on a vehicle being present at the location. Maybe now show you a video.
In this visualization, we show the rasterized map given to the model as input. On top of the map, we overlay the ground truth actor bounding boxes, which are not given to the model. First, we show a video with 2 seconds of context surrounding the scene. Our model is trained to answer questions relating to the center of the snippet. Question 1, is there a vehicle turning left in the intersection? Both our model's answer and the ground truth answer are yes. We can see the vehicle our model classifies as turning left in yellow. Question 2, how many pedestrians are in the intersection? To obtain an answer, our model first regresses a density at each spatial location. Here, we overlay our pedestrian density estimates at each spatial location. By pooling over the intersection region, we obtain our model's answer. Our model, 17.8, ground truth, 17. Let's move on to another scene. First, we'll show 2 seconds of context. Question 1, is there a vehicle braking for another vehicle behind the self-driving vehicle? Both our model and the ground truth answer yes. Question 2, how many vehicles are in the entire scene? Once again, we overlay our model's density predictions at each location. We sum the values over the entire scene to obtain our answer. Our model, 48.6, ground truth, 45. Let's move on to a final scene. Again, we'll show 2 seconds of context. Question 1, what is the maximum vehicle speed in the scene? We can answer this with a compositional query. First, we compute the vehicle speed at each spatial location. Next, we compute density at each spatial location and use a threshold to mask out regions without vehicles. Finally, we multiply the 2 answer maps and max pool over the scene to obtain a final answer. Our model, 15.9 meters per second, ground truth, 15.8 meters per second. Next, we'll show a failure case of our model. Question 2, is there a vehicle performing a right lane change anywhere in the scene? Our model answers no, while the ground truth is yes. Let's rewatch the scene to see why this question is difficult for our model. Pay close attention to this actor, as it will perform the missed lane change. Notice that for some frames, the actor is fully occluded. Also notice that at time t equals 0, the vehicle is just at the beginning of changing lanes, making this classification more difficult. If we ask the same question 1 second later, our model correctly answers that the vehicle is changing lanes. Thanks for watching our video.
We also test our model in the retrieval setting. For example, in the first row, we show logs that our model retrieves when asked to find examples with more than 10 vehicles around the SDB. In the second row, we show visualizations of retrieved scenes at a freeway intersection directly in front of the SDB. Finally, in the last row, we show examples of other actors turning in front of the SDB. Next, we will move into human-in-the-loop labeling. As we know, deep learning algorithms require a huge amount of data. Rather than annotating everything from scratch by manual labelers, a semi-automatic approach with the annotator in the loop can speed the labeling process and make it more scalable. As an example, we show this for the task of instance segmentation. Our goal is to perform instance segmentation, that is, label each object in the scene with its own instance ID. In the interactive annotation problem, we are given the ground truth bounding box, and we want to predict the polygon mask. The goal is to create labels automatically for human annotators to correct instead of just annotate from scratch. Current instance segmentation methods output masks that are coarse and do not have good boundaries. Instead, we present a novel approach to instance segmentation that deforms and refines a set of initial an initial set of polygons. Towards this goal, we can leverage any instance segmentation method to generate an initial set of polygons for each instance. In particular, we use UPSNet to generate initial mask and use a line following algorithm to extract the initial polygon. Next, we crop the instances using the detection from the initial instance segmentation method and feed it through a feature extraction network. This feature extraction network outputs an image embedding representation of the instance. We can then use the coordinates of the initial polygon to sample from the image embedding using linear interpolation. This results in a vertex embedding representation of our initial polygon. Finally, we feed the vertex embedding into the transformer network. This is a self-attending network that allows for the vertices to communicate with each other. This network learns for each vertex which of the vertices are more important and should be weighted more during computation. The network then outputs the offset for each vertex. We take this and add it back to the initial polygon to output the final polygon prediction. We show results in the fully automatic setting here on the Cityscapes test leaderboard. We see that at the time of submission, we achieved state-of-the-art between the previous methods by 3.7 AP. We also show our results on our internal dataset. We see that we also significantly outperform all the baselines, so this generalizes well across datasets. We also run experiments with 150 images and have annotators annotate from scratch versus using our predicted polygons as initialization. When using our predicted polygons, annotation speed was 35% faster and therefore cheaper. We also visualize the precision and recall of our control, which is annotating from scratch, versus annotated using our predicted polygons. We see that the precision and recall with different IOU thresholds are around the same. This suggests that annotating with our predicted polygons is just as good as annotating from scratch. We also show the results of our model in the human-in-the-loop setting of Cityscapes. We see that we perform the corner state-of-the-art in this setting. We also improve the boundary metric by 2%. Here we show the results of our model run on a video. This is in the fully automatic setting. Our model performs very well, especially at the boundaries. As you can see here, this is a very challenging scene, very crowded with many instances, and despite this, our model is able to estimate almost all of them. Next in the agenda, we will move on to high-definition mapping for autonomous driving. We will explain how HD maps are created, where annotators come into play, and how machine learning algorithms can be used to scale mapping. High-definition maps are of high importance in self-driving applications. They contain both detailed geometry and semantic information about the environment and are used for precise localization of the self-driving vehicle, as well as prior knowledge for the autonomous system and for simulation. The first step in mapping is to create accurate geometry. In the industry, many passes over the same area are required for those maps to be complete. However, we would like to reduce this requirement as this is very expensive. Furthermore, maps typically require large amount of memory to be stored, preventing them from being able to be produced and used at scale. Finally, we would like the maps to only contain permanent elements that will be seen every time we drive in this map area. Thus, we would like to remove things like pedestrians, vehicles, etc. Building geometric maps is typically a three-step process, where the data is first collected by the fleet of vehicles. Then the data is uploaded and the process is decomposed into trajectory fitting of small chunks, which can be performed in parallel. This is then combined into a massive global optimization problem, which can be solved, for example, with graph slam techniques. The result is high fidelity maps of our cities. In this video, you can see the construction using both LiDAR as well as cameras. Here we have removed elements, for example, vehicles, that most likely will not be there next time they will arrive. HD maps contain also very rich semantic information. This includes the location of traffic lights, lanes, crosswalks, as well as the routes of traffic at each intersection and road segment. In order to create semantic HD maps at scale, we need to design approaches that can leverage both machines as well as humans. Humans are necessary as the level of fidelity required in self-driving is way beyond what the state-of-the-art can do. Self-driving companies are particularly interested in designing approaches where machines and humans can collaborate to minimize the total dollars spent. Knowing what the road boundaries are, that is, delineating the separation of the drivable surface of the road from sidewalks, is crucial for safety and navigation. Currently, in the industry, human annotators draw these road boundaries from scratch as part of the high-definition map production. This is a very expensive task since we need to annotate whole cities, and as such is not scalable. In this work, we aim to automate the annotation process so that human laborers only need to do QA and adjust the wrong predictions or draw the missing boundaries rather than annotating everything from scratch. We tackle this problem by directly outputting polylines for each road boundary from BEV inputs. The input to the model is the LiDAR and BEV imagery and LiDAR elevation gradient. These are inputted to a deep convolutional network that outputs visual cues on the position, endpoints, and direction of the road boundaries. Then, a convolutional RNN iteratively attempts to rotate the regions of interest in the image and outputs the vertices of a polyline corresponding to the road boundary. The direction of travel of the RNN is obtained from the direction map. We obtain all the road boundaries one by one as such. In this video, we see the results of our model on the test set. On the left is the in red is the ground truth road boundary polylines. On the right, we see the output of our model. In this case, this is the fully automatic setting. The yellow rotated boxes correspond to the regions of interest that the recurrent CNN attends to sequentially. The blue dots are the predicted vertices. Note that all intersections and areas of high curvature, the model has learned to place more vertices closest to each other. We also tackle the problem of automatic drawing crosswalk boundaries. Existing approaches focus on predicting the existence of a crosswalk, but do not provide an accurate localization. Instead, crosswalks are typically crowdsourced and manually drawn. Here we draw crosswalks as polygons. Our model takes as input the LiDAR and BEV imagery that is fed into a CNN to output inverse distance transform, segmentation, and angle alignment heat maps. Next, we take advantage of the road boundaries that have already been drawn and exploit the structure prediction to create the final drawings. By leveraging distance transforms and integral accumulators, efficient exact inference is possible. Our model achieves 96.6% automation of crosswalks. In this video, we showcase our model results, top right, compared to the ground truth, bottom right. We see that our model draws very accurate crosswalks when compared to the ground truth. And this can be directly used for production maps. Next, we tackle the task of drawing precise lane boundaries. We focus on highways which offer interesting topologies. Instead of requiring multiple passes of the vehicle, which is costly, as is typically done in the industry, here we aim to draw from only one pass of the vehicle through the area. We formulate the problem as discovery and inference in a directed acyclic graphical model, that is a DAG, where the nodes correspond to geometric and topological attributes. Given a temporally aggregated LiDAR point cloud projecting into Versailles view, we aim to find the maximum a posteriori of the probability of all the possible DAGs that could describe the road. The probability distribution of each DAG can be factorized as the product of the probability distribution of its vertices and each vertex conditioned on its parents in a random and each vertex conditioned on its parents is a random variable with the following three attributes: the direction of the vertex given the parent vertex, the geometrical positions of the vertex, and the topological state of the vertex as in no change, fork, merge, and stop drawing. The space of all possible graphs is exponentially large. So we greedily construct the graph and compute the geometric and topological properties of each vertex. We demonstrate the inference process with the figures on the right. On the top, assume we have the already inferred DAG at the current timestamp. Next, we find the direction of the next vertex highlighted in the yellow rotated region of interest. Then we infer the position of the vertex in the ROI and a state which is inferred to be a fork. At this fork, we continue drawing the correct lane boundary as is, but emanate a new one corresponding to the new lane boundary at the fork. Of course, all our potentials here exploit deep learning features. So this is a deep structure model. Finally, we show the results, we show the output of our model on long stretches of the highway. This is around 500 meters for every one of these images. As you can see, we can produce very complex lane topologies and achieve a very, very high degree of automation. This can save millions of dollars for self-driving companies. So to conclude, we show how to create end-to-end solutions to self-driving that produce interpretable intermediate representations. We then show how machines and humans can collaborate to understand logs captured by the fleet, as well as to create labels and high-definition maps at the scale. This is all for me today. Thanks for listening.